I think 1-1 and 1-2. We definitely should finish up 1-2 for sure. 1-3 and 1-4. I'm gonna have to do a little bit from both just to make each one make sense. I think I warned you this author sometimes does things, and then the next section he actually explains how to do what he did. So, yes.
You said that 3 days a week from today. Isn't that a holiday?
So okay, in reference to the class. So,
Oh,
so like, what is today? Today's Monday. Yeah, next Monday is a holiday, so I mean next Wednesday. Yeah. When is our first? Our first test is scheduled for March 3rd, I believe. Yeah, sounds about right. This is why I write it all down, because I can't keep it in my head. So it's up on the homework sheet. Thank you. Thank God. Verification, validation. Is everybody with me? So we'll have our first quiz, 1-1, 1-2. Next Wednesday, next Monday is Washington's birthday, maybe? Some president's birthday. We're like, yeah, let's take it down. You know, you can have your Washington tree up. I don't know. I think it's also Lincoln's birthday somewhere. I don't know. So, anything else? Anything else from homework or just general stuff about the class? Yeah.
Are there like, do you post videos on Canvas that would also help us? Is it under the inside the syllabus?
I'm sorry.
Did you like post any videos that might help us understand more about vectors and matrices, or any videos in general besides the lecture?
Oh, I could. I think I did put like the resources link that I showed you guys at the, and if you have any suggestions, I can add to it, right? You could search, in fact, I need to do this still. This is one thing I want to add. The author has made his MIT lectures available for everybody for free. So you can search Strang linear algebra lectures. I think they have them up on YouTube, but I think they're also through MIT. So you can, pretend like you're at MIT where they have these giant chalkboards, and I'm just very jealous. I miss my chalkboards. And, you go to the top of the thing, and you're like, oh my god, I gotta get one of those weird ladders to go up, and so you can ride at the top. But yeah, I mean, if anybody finds a YouTube channel, something that you like that seems to explain things in a way that you get, if I can't do that, then I understand going out for other resources. Trust me, that's what got me through grad school. Because sometimes you have a teacher that totally says things the way you think, and then you get a teacher's like, that is not how I think. So then you have to find somebody saying the exact same stuff in a different way, right? Okay. Now, real quick, this class is incredibly short, and we've done so little. The first day was a lot of syllabus and talking about how the course is going to work. The second day was cut short because of our little field trip, and that was exciting. So we haven't really done a lot. We haven't even gotten to the section 1-2 yet. So we'll do that. Anything else? Question about homework or yes?
How long are the quizzes?
Normally like 6 questions long or so. 6. It depends on how long the material is. Sometimes they do like a 1-question quiz because the one question has 8 parts to it. You know what I mean? For a first quiz, it's going to be pretty, nuts and bolts stuff. So I'd say like 6 questions or so. Yeah. I try to design them to take about 20 minutes at most, 20, 25 minutes or so. Yeah. Okay. Anything else? So if you missed it, let me get this all official. Ooh, I'm recording. What is next Wednesday? What is today? Today's the 10th? 17th? 19th? 19th? This will be on 1-1, 1-2, and probably soon after that we'll have one on the next couple of sections, depending on how our pacing is. Okay. I love it. So if there's no questions from homework stuff, we assume that's a good thing. Let's get right back into where we left off. I think I pretty much finished section 1.1. And if you feel like things have been a little amorphous, you are not wrong. It's just the nature of the beast. We have to lay down some groundwork. We've been talking about dimensionality, right? We've been talking a little bit about can I cover a plane? So for example, if I wanted to cover the entire XY plane, let me ask you this question. Can somebody give me two vectors in the XY plane that linear combinations of them would not cover the entire plane, would not cover the entire XY plane? Yeah.
1, 0, and 2, 0.
1, 0, 2, 0, right? With 1, 0, 2, 0, there's no way to go up and down. You can only go left and right. Because linear combinations allows for negative multiples, yes? So those two vectors, I could create the x-axis, but I could not make any off-axis points. Does that make sense? So then what does it feel like must be true? And let's go to all dimensions. In 2 dimensions, how many vectors do I need? What's the least number of vectors I need to create every vector in R2? And what must be true about those vectors? I need 2 vectors. And what's the most basic vectors I could use to create every point or vector in R2? IJ. 1, 0, 1, and 1, 0, yes? So 1, 0 is on the x-axis. That was what we affectionately call I, with a little hat on it. So in 2D, this will be 1. Let me write it like this is going to be exciting for me. 281 covers a lot of the same material 284 does at the beginning. 284 then kind of takes a turn, and 281 takes the other turn. We use very specific notation in here because it matches with the turn we're going to take. And we use very different notation in 281 because it matches with what we're doing. In this class, I got to remember, vectors are like this. So I would be the vector 1, 0. J would be the vector 0, 1. If I'm in R cubed, I would be 1, 0, 0. J would be 0, 0, 1, 0. And K would be 0, 0, 1. Okay. Some of you guys might have come in knowing some of this, possibly, or not. But that kind of makes sense. It lines up with our y-axis, our x-axis, y-axis, z-axis, and combinations of those will create points or their associated vectors. Let me stop for a minute. Hey, what's true about the XYZ axis? What's true about the x-axis versus the y-axis? What's the angle between those two? 90. And I believe I talked to you guys. Do I need, so the angle between I, J, and K, or I and J if you're in R squared, those angles are 90 degrees. Because it makes sense to construct points or vectors. I want the most basic building blocks. And that makes it stupid. If I want to construct 3, 2, 1, I use 3 I's, 2 J's, 1 K. Do they have to be?
Sorry.
Go ahead.
This is more conceptual, but if all of the axes are orthogonal to each other, so in the case of R4, would that axis be orthogonal?
Totally. Mathematically, I don't have to be able to draw a picture of what I'm talking about, right? I think I talked to you guys about Pandora, the music. Yes. So a jazz song has 500 components. So mathematically, I can consider each of those components to have its own axis. It's completely own axis. The math doesn't give a shit. So if I wanted to know the distance between 2 points in R73, I would just go the square root of x1 minus x2 squared plus y2 minus y1 squared plus z2 minus z1 squared plus a2 minus a1 squared plus b2 minus b1. 78! You see what I'm saying? The math doesn't care. We care when we're trying to be like, what does that look like? So I talked to you guys a little bit about every point in this room. I could designate it with 4 coordinates. 3 physical, 1 temperature, correct? You guys with me? I could make a 5th. I could talk about the barometric pressure. I could make a 6th. I could talk about the humidity at every point. You guys see what I'm saying? You guys see what I'm saying? That is a 6-dimensional space that we have no problem conceptualizing physically, do we? Because they're not 6 physical dimensions, not in terms of direction of motion, yes? I really want you guys with me. So a 6 dimensions physically is hard for us 3-dimensional beings to understand, yes? But the math didn't give a shit. Okay, maybe, I don't know if that really helps. But that's yeah, okay. All right. So I think last time I was trying to talk about dot product and how it eventually gets to the angle between 2 vectors, if I remember correctly. So what I want to do is I kind of want to come at it a slightly different way because I started doing it the way that I did it in 281, and I want to do it a slightly. Yeah, sorry. Oh shoot! What happened to you, poor little guy? Oh man, he's dead. Let's see if he likes the PC. No, he doesn't like anything. He's just dead. Poor little guy. All right, give it a second. Have you tried turning it off and turning it back on again? If this doesn't work, I'm going to open something and blow on it. Oh! Hey, all right, thank you. I didn't even notice, I'm sorry. Yeah, please let me know when things like that are happening. Don't take it like, this guy sucks, he doesn't even want me to know what's going on. There's also a mantra that's not very useful, but okay. So let's do this. First thing I want to do is, if I have 2 vectors, and I'll say, it's very bright. I'll say that, let's say that V is V1, V2, V3, and W is W1, W2, W3. V dot W is V1, W1 plus V2, W2 plus V3, W3. So right now I'm in 3 space, I'm in R cubed, but this could easily be extended to anything. So what's true about V dot W? Now, okay, very quick. I'm gonna say this several times. All my 281 people, we just talked about this today, so should be on it, but what's the output for a dot product of 2 vectors?
Scalar?
Scalar. It's a number, it's a scalar. I love it. Somehow, this is gonna relate to the angle between the vectors. So I'm gonna do it a slightly different way. And it kind of relates to other things we have to know anyway, so it's perfect. If I have a unit vector, let's go back to R squared. And everything we do here is just scalable up to whatever dimension you want to be in. If I have a unit vector in R squared, what does that mean? Do I have to be on an axis? I just have to, a unit vector is one where the length is, yes. So I just need a vector of length 1. So could this be a unit vector? Yes, depending on my scale. So let's all pretend that has got a length of 1. Kick ass. Can somebody tell me what this is if I call this alpha, just to be different?
Cosine of alpha.
Yeah, cosine alpha. And what's this?
Sine.
Holy shit. Because, you know, in general, this isn't true, but it works. Cosine is kind of like the percentage of the hypotenuse is in the x direction. Sine is kind of like the percentage of the hypotenuse in the y direction. It's not true because it's not a linear relationship, but it's kind of nifty to remember. If I have a hypotenuse of 17, cosine of the angle is the percentage of 17 in this direction, so it's 17 times cosine of the angle, 17 times sine of the angle. A lot of you guys should know that. Okay. So if I have a unit vector, let's call it u, that's insane. And so this would be the vector sine, Jeff, you can do it, cosine alpha, sine alpha. What if I have a different unit vector that's pointing over here, and its angle is beta? Beta. I'm going to call, let's call this one U1, and we'll call this one U2. That's crazy sauce. So what's U2 then? Let's do it again, sorry.
Negative cosine.
No, don't overthink it. Don't overthink it. Beta is also from 0 degrees. So if it's over 90, it's going to have a negative baked in. Yes? You don't have to put the negative. Well, I appreciate it. Does that make sense? Cosine of 110 degrees. Is it positive or negative? It's already negative. So I put the first vector in the first quadrant. Did I have to? Would that have changed my U1 at all if I put it in any quadrant? Nope. It would have been exactly the same expression because the negatives are baked in. So what is U2? Cosine.
Alpha plus beta.
No. This whole thing is beta.
Oh, beta.
Yep. Cosine beta. Sine beta. Okay. Love you guys. What is, so that is every single pair of unit vectors. I've just written them all down, right? So if you also wrote them down, we just wrote down an infinite number of vectors. Thank you very much. It's a pretty good afternoon. We're going to do more though. Can you guys really quickly do U1.U2?
Alpha minus cosine alpha minus.
Ooh,
Beta.
look at you getting ahead of me. Okay. Anybody else got the dot product? The great thing about the dot product is you just multiply the corresponding parts and you add them together. That's the main idea of dot product. Like I put here. Bam, 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 bam. We're only in 2D, so it's awesome. So it'll be cosine alpha, cosine beta, plus sine alpha, sine beta. V got one step ahead of me. There is a trig identity that this can be reduced by something. This can be written more compactly. I don't know if anybody had me for pre-calc or whatever, but one of my favorite things in pre-calc is to point out that cosine is an asshole. Cosine of A plus B. Does anyone remember cosine A plus B?
Cosine minus sine.
Yeah, cosine's an asshole. Me first. Cosine, cosine, cosine A, cosine B. You got a plus, I'm going to make it a minus. Why? Because I'm an asshole. Minus sine A, sine B, right? Does that sound at all familiar? Cosine of A plus B equals cosine A, cosine B minus sine A, sine B. You guys said my way. Doesn't that, what's cosine of A minus B? Cosine A, cosine B plus sine A, sine B. Yes? So what's another way to write this more compactly? Cosine's an asshole, that's a plus, so of course what must have been there in the first place? Minus, and what am I subtracting?
Alpha beta.
Something else to realize about cosine? What's cosine of negative theta? Cosine theta. Because the x-axis, theta is here, cosine's positive, negative theta is there, cosine's still positive. So cosine of theta equals cosine of negative theta. I love you guys. Some of you guys are, sorry, some of you guys are looking at me like, this makes sense. Okay. A lot of what I'm talking about right now is built on trig identities. It's possible you've forgotten some of them. I'm hoping some of this sounds familiar, yes?
Can you write down the cosine AB thing?
Sure. So in general, cosine of A plus or minus B is cosine A, cosine B, that's why he's an asshole, minus plus, it turns that dumb thing around, asshole again. Then sine, you get a turn because I'm all done. Sine of A plus B, sine's a nice guy, plus or minus, will be, let's take turns cosine. Oh, thanks, sine. Keeps it the same, and then they take turns. Okay, maybe. Does that sound at all? Now, of course, your teacher probably didn't talk about cosine being an asshole, because that's a weird thing I do, but it's just a thing I noticed. It actually carries, because what's the derivative of sine?
Negative.
No, what's the derivative of sine?
Cosine.
Cosine. What's the derivative of cosine? Negative sine. See, cosine's still an asshole. So you can kind of extend the idea that cosine's an asshole, actually extends across a lot of what cosine does. It's kind of neat. And we kind of made it an asshole, so it's not its fault. Poor little dude. Is that okay? Those are the basic trig identities from before. So we just applied one in reverse. And also, isn't this equal to this? Jeff, you can do it. Like we just said, cosine of theta is equal to cosine of negative theta. Okay, so you're all like, go Jeff, you're playing around with shit, fantastic, good job. What's this got to do with us? What is the angle between the two vectors up here? Somebody beat me to it a little bit earlier, but maybe accidentally.
Beta minus alpha.
Beta minus alpha. So what did we just discover then? If I have two unit vectors, their dot product is equal to the cosine of the angle between them. So more generally, I can say if theta is the angle between u1 and u2, u1 dot u2 equals cosine theta. That's kind of powerful. That's insane. If they are unit vectors, their dot product is equal to the cosine of the angle between them. That is trippy. If you really think about it, that is exceptionally trippy. Because how do I figure out what a dot product is? I just multiply the corresponding components together, and somehow that equals the cosine. That's crazy shit. So can somebody give me a unit vector? Without a zero in it. Let's do this. A unit vector without a zero in it. You can do it, yes.
Square root 3 over 2, 1/2.
Yes, square root of 3 over 2, 1/2. Somebody else, give me one that's different.
Wait, isn't the notation supposed to be different?
Oh yeah, sorry. I appreciate that. Square root of 3 over 2, 1/2. And then let's say u2. And again, the reason we do that in linear algebra is because our entire world is going to be dominated by matrices. And our vectors are just going to plug right into matrices. So that's why we want to write vectors like this. If you take it my 281, good luck. Because there we write it like I just did. Somebody else give me another one? You can do it. What's the cosine of 45 degrees?
Root 2 over 2.
Yeah, so let me do negative rad 2 over 2 and rad 2 over 2. Is that cool? Are those both unit vectors? How would you verify? You would find the length, yes? So the length would be this squared plus that squared. That's 2/4 plus 2/4 is 4/4 is 1. Square root of 1 is 1. Beautiful. Okay, nothing amazing. So if I take the dot product of those two, I should end up with the angle between them. So what is u1? I'm sorry, the cosine of the angle between them. Let me be very careful. What is u1 dot u2? You can do it.
Root 3 over 2 times.
Yeah, so it'd be negative rad 6 over 4. Is that cool? Do you guys see that? Negative rad 6 over 4 plus. How do you do dot product? You take the x components and you multiply, then you add it to the y components multiplied, and you add it however many dimensions.
Root 2 over 4.
Root 2 over 4. Really quick, for U1, what angle are we talking about? What angle makes cosine rad 3 over 2?
30 degrees.
30 degrees. For U2, I'm negative x positive y. What quadrant am I in?
Quadrant 2.
Quadrant 2. What angle am I talking about? Yeah, this reference angle 45 degrees, so this angle would be 135 degrees. So the angle between them should be 105 degrees, yes? Okay, let me stop for a minute. I love you guys. I'm going to feel very rushed in here, so I'm sorry. If I ever go too fast, slow me down. If I ever go too slow, just deal with it. Can somebody in your calculator, what is the dot product we did? What is the square root of 2 minus the square root of 6? All of that divided by 4. What is that? What is this? Roughly.
Negative 0.2 something.
Is that what you got?
Negative 0.2588.
0.2588?
Yeah.
Okay. Now what's the cosine of 105 degrees?
Negative 0.2588.
Kick ass. Okay, good. It's always nice to verify something you got theoretically with a nice concrete example. So again, if I have 2 unit vectors and I take the dot product of them, I end up with the cosine of the angle between them. That is silly. That's silly. If you think about it, dot product. How hard is that to do? Not. And then you end up with the cosine of the, what the shit? So all I do is I multiply things and I add them together, and I end up with the cosine of the angle between. Holy crap! I don't know. Somebody, you're reacting enough for all of us. So it's whatever. To me, that's insane. That's amazing. Now, does every vector I work with? Is every vector I work with a unit vector?
No.
How can I create a unit vector out of a vector I'm working with? Yes. So if I have 2 vectors, u and v, and neither one is a unit vector, I can just take u divided by its length. Sorry. This is another thing that's left from dotted with v divided by its length. And that should equal the angle of the cosine between them, right? Because now I have 2 unit vectors, don't I? Therefore, u dot v equals the length of u times the length of v times cosine theta. So that is the, if you're in my 281, we developed that equality. We have developed this relationship in a very different way. Stop for a minute. So if I give you any 2 vectors in the universe, you could figure out the angle between them. I don't care how many dimensions it lives in. You understand what I'm saying? 2D. What can I use to figure out the angles between any 2D vectors? Frickin' trig. Yes? I don't need linear, Jeff. Your linear shit. The minute I get to 3D, screw your trig. Yes? So if I give you 2 3D vectors, so if I give you v, w, what's the angle between those 2 vectors? That's here. Yeah. So
you do V dot W over the length of V times the length of W, that's the cosine of the angle. That is independent of dimension. That is just a true statement. And it might freak you out a bit. Do you all agree that those two vectors live in 3D, three dimensions? But don't those two vectors themselves define a plane? If I have two vectors, I don't care how I orient them, there's a plane that goes, there's only one plane that they both live on, correct? So in that, the same sense that 2 points define a line, 2 vectors define a plane. And so in some way, every two, I don't care how many components the vectors have, how many larger dimensions they live in, they actually end up together living in some kind of two-dimensional space. It's a plane they live in. I don't know if you guys are really with me. That's one reason why the mathematics we do here doesn't matter how big the dimensions get, because eventually they kind of boil down to 2 dimensions. They define one plane they live in. What'd you guys get? What's the dot product? I get -5.
That's probably wrong.
2 minus 3 is -1, minus 4 is -5. Is that cool?
That's what I got.
The length of V, root 26, and the length of W, oops, what's that doing over there? 4, 5, 6. And that's cosine of theta. So how do I figure out what theta is? Inverse cosine of blah, 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 whatever the hell all this shit is. Yeah. What is it?
113 or negative 113?
113?
113 or negative 113.
Well, 113. There is. Yeah. And I guess technically you could say negative 113. It depends on what you're defining as your starting point, but we just always say 113. Yeah. All right, let me stop for a minute. That is a very truncated version of the lecture I gave in 281 because in this class that's not quite as important immediately. This is like a little offshoot of vectors, vector and dot products. So what's true if I have two, well, actually let me do this. If I have a vector in 2 space, this vector, AB. Can you give me one way to represent that? What's got to be true? The vector must be pointing at the point what? AB. So it doesn't have to be in the first quadrant, but for simplicity I'm going to do this. In fact, I could even be in whatever quadrant. I've just turned it to look like this, yes? Okay. This is A, and this is B. So it's the vector AB. Can somebody tell me the slope of the line that vector is on? Yeah, B over A. Rise B, run A, yes? What is the perpendicular slope? Can anyone tell me the vector that negative A over B that line would be lying on? So now it's, actually, I should be, let's see if I could do this right. Yeah, negative A. No, Jeff, you could have, in order for, I could put it down here. Okay, that might be better, based on what I've done here. So this would be negative A down and B over, yes? Just to match it with the slope, and it's got a 90-degree angle because we made it perpendicular, correct? So the vector would be what again, I'm sorry?
Isn't A the x coordinate?
Say again?
Isn't A the x coordinate?
Not here, because what slope? Y over x. So wouldn't the y be the A here now?
Oh.
Okay, good,
Yeah.
good. So what would the vector be? B, negative A is the school? Okay, I love you guys. I love you guys. You all agree with me that the vector AB would lie on a line whose slope would be B over A. The perpendicular slope would be negative A over B, which vector B, negative A would lie on. If I do the dot product of those two things, what do I get? You get AB. You can do a dot product of those two vectors, AB and B negative A. What's the dot product? So the vector AB and the vector B negative A. What's the dot product? AB minus AB. Zero. Right? Which matches up with what we know must be true. If two vectors are perpendicular, the angle between them is 90 degrees. What's the cosine of 90 degrees? Freaking zero, yes. So dot product, this is what I said last time. Dot product wants to multiply the components of the vectors that agree with each other. If there are no components of the vectors that agree with each other, the dot product will come out to be zero. Another way to say what I just said is, if they are perpendicular to each other, the dot product will come out to be zero. So I can make an if and only if statement. The dot product is zero, if and only if the two vectors are orthogonal or perpendicular. Yes? Maybe. Oh, cool. Did that. So let me ask you about this. And here's one reason why in 284 we designate the length of a vector this way, right? Whereas in 281 we actually just use that. Here's one reason why. Could V dot W be negative? Yes. Yes, right? And what we just say V dot W is V W cosine theta. Is that cool? Okay, I love it. I love it. Okay. And what's the biggest cosine could be? 1. So therefore, the absolute value of V dot W. Now in Math 281, what I just wrote would not make much sense. Because you can't talk about the length of a number. The length of any number is 0. The length of the vector is 0. So that, for us, means absolute value, like it always has. And I think I told you guys, the double one is the standard way to do it, but for some reason our Stewart book for 281 just uses the absolute value symbol, which, oh, I'll get over someday. I really want you guys with me here. Help me out. What's the absolute biggest that V dot W could be?
Magnitude of V times the magnitude.
Yes, because the absolute biggest the cosine could be is 1. So therefore, the absolute value of this is at most V dot, no, not dot, times the length of W. This is given credit to Schwartz. Forget his first name. Sorry, Schwartz. Pretty sure it wasn't John. John Schwartz. Schwartz inequality. This one's kind of like, yeah, we'll name it after you, but it's not that big of a deal, to be honest. The one that's a little bit more of a big deal is this inequality. And in one sense, so you could prove this by looking at, well, let's see. If you did this would equal, let me see if you guys are cool with this. Let me see if I've written this down yet. Quick side note. What is V dot V?
V squared.
Magnitude of V squared.
Yeah, magnitude of V squared. I couldn't remember if I had made that official or not. So what is the magnitude of V plus W squared? It's V plus W dotted with V plus W, which is V squared plus W dot V plus V dot W plus where'd it go? W squared and do you see how this is actually equal to something bigger than let me see, how do I want to say this? Yeah, I could do this. I don't want to get all into the weeds here, but this I can rewrite as the length of V, length of W cosine. Let me see if you guys cool this. Actually, I could just use, okay, here's a short one. The length of this, which is what I really should have here, but we'll be okay, is less than or equal to the length of both multiplied together. I don't want to get too deep into this. Less than or equal to this. And that is equal to the length of V plus the length of W. Do I have this the right way around? I think so. That whole thing squared. Yes. Okay. Yes! And if I square root both sides, I end up with this inequality. Yeah, here. This one is called, don't worry too much. I just want to do this really quickly just to show you. You can actually work this out. This one, not surprisingly, if I show you a different way to think about this, is called the triangle inequality. Let me ask you this. If you try to develop this three sides of that makes a triangle, what do you have to be careful about? Can you just plop down any three numbers and they'll make a triangle with three sides?
No.
Isn't it possible, you guys remember, I'm sure, the situation where there's this, if you have one length and another length and this length is not big enough? Oh no! It's just not going to make a triangle. This is even worse than that. Could the lengths 3, 4, and 8 make a triangle? Why not? Because even if I make it straight, that's 7. So the absolute biggest from 3 and 4 is 7, and that wouldn't even be a triangle, that would just be a flat line, correct? So the sum of any two has to be less than the third one, which is basically what this guy is saying. It's saying if I have a vector v and a vector w, and I'm trying to construct, and then v plus w would just be this guy. See how I get a triangle here? This guy's length has to be less than or equal to the sum of these two guys' length. That's why we call it the triangle inequality. It's sort of a vector version of that idea. Any two sides can't add to be more than the third side, or else you can't make a triangle out of it. Okay. Or less than the third side. Okay. All right. I didn't want to focus too much on that, but I at least want to show you it can be proven. Very quick thing about planes in 3D. Can everybody take your pencil? Does everyone have a pencil of some kind? Stylus, I love it. Take your pencil-looking thing and just put it straight up and down on your desktop. If you consider this to be a vector, this, how does it relate to every vector that it lives in the desktop? So if I do this on the board, right? So this is your desktop. How does this vector relate to every vector that lives in the plane of the desktop?
It's a cross product.
Don't put a cross product yet. It's perpendicular, correct? You put it straight up and down, so I kind of inherently told you to make it perpendicular. So, if I want to describe a plane in 3 dimensions, I just need 2 things. And some of my 281 students, I think we made it this far, didn't we? I just need a vector that is what we call normal, meaning it's orthogonal to every vector. and 1 point. So real quick, if I'm telling you this pen is my normal vector, it's orthogonal to every vector. Where's the plane that is orthogonal, that has vectors orthogonal to this? Is this one plane that could be true? How about this one? How about this one? Yeah, there's an infinite number of them, correct? So if I want to identify, but aren't they all oriented a certain way? If I move this, don't they have to move? So I have determined one aspect about a plane, but I've still made it too open. It could be any of these, yes, running up and down, but I really, it can't be this plane. Nope, it's got to be something like this. And if I give you 1 point in the plane, now that's set, yes? The same way if I give you a point and a direction, I define a line, yes? Well, if I give you a normal vector and a point, I define a plane. So, if I consider, this is a little bit different from that, let me see. If I have a normal vector, let's talk about, 3D. And my point, for now I'm going to make my point 0, 0, 0. So then, if I look at my normal vector dotted with every vector in my plane, by definition, what should I get? I should get 0, yes? So far I've really done like nothing. Of course that's going to happen because that's how you freaking define n. It's a normal vector to all the vectors in your plane. It's a fantastic job. If I write this, let me see, I want to write the same way the book does. I already did. There it is. Good. Let's call W. This is going to blow your mind. W1, W2, W3. What is n dot W?
Would be NW, N1, W1.
W1
Plus N2, W2.
2, Jeff.
Plus
You had 1 job, Jeff. So if I write this, now, real quick, which one of these two represents an infinite number of things? This one does, yes? So let me write this one a little more like what we're used to. Yes? And then, if I feel like being nice, I can call my normal vector, I can actually go ahead and say, well, let's like our normal vector A, B, C. Then I get AX plus BY plus CZ equals 0. That is the equation of a plane. And just to mimic something I did with my 281 students. So if you're in 281, it's really weird. In this class, we sometimes get ahead, and right now I'm going back to something we already did in 281. You guys are probably knew this. When you talked, very quickly before I do what I was about to do, when you did systems of equations, 3 variables, 3 unknowns, right? 3 unknowns, 3 equations, yes? If you did 2D, you could draw a line, and the answers were they met. You guys remember that business, right? So when you're in 3D, your teacher hopefully did something like this. The first equation could be that wall, that plane. The second equation could be that plane. And the third equation could be the ceiling. So the answer would be that point. The corner point, yes? That's the point where they all meet. Inherent in that was the fact that 2x minus 3y plus 4z equals 11 was the equation of a plane. And you just sort of like accepted it. Yes? Does it sound familiar at all to anybody? Okay, so very quickly, I just want to show you something kind of nifty. If I add x plus y equals 0, what does that create in the xy plane? That's insane, yes? That's amazing, John. What if I add x plus y plus 1 equals 0? What does that do? You gotta be. Yes, it would shift it down by 1, yes. So then it would go here, yes? And if I said x plus y plus 2 equals 0, it shifted down. If I said x plus y minus 1 equals 0, it shifted up, yes? Now they should all be parallel, give me the. Now, if I said, okay, I don't really live in 2D, everything I just did was in 2 dimensions. What if I said, no, I live in 3D, and this thing I kept changing the value of is that third variable, which only makes sense. That's what a variable does. I change the value of the damn thing. But now I'm in 3D, so when z is 0, where am I? In the xy plane. So then in the xy plane, for this equation, in the xy plane, I'm going to have the equation y equals negative x. So it's going to look like that. And then if z equals 1, I'm going to be lifted up by 1, but down 1 on these. So it's going to make this slanted. It's a little difficult to draw in 3D. So everybody just take a moment and have a thought for my poor 281 students. It's going to be a slanted plane, but every time you take a step up on the z-axis, it's actually going to step down on the xy axis. So it's going to be a slanted plane. You guys see that? So I could start with 2D and then feed the third d in as another variable, and you can kind of naturally see how that creates a plane. Every time I have another z, I get another line. And what is a plane? What's one fundamental way? How do I 3D print a plane? Line, 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 right? Sorry. That's the way the 3D printer sounds. Okay. Have you guys ever seen the 3D printer go? Who was the printer? Okay. Okay. Enough. We don't have time for all that, Jeff. So, blah, 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 blah. Perfect. Yeah, okay, beautiful. Yes, okay. Now, that's basically section 1-2, believe it or not. 1-2 is about dot product. It introduces the basic idea of a plane equation being ax plus by plus cz equals 0. Now that is a plane that contains 0, 0, 0. What do you think would change if it was a different point it contained? Ax plus by plus cz equals 0 contains 0, 0, 0. Yeah, it just changes 0. Bless you. Or you can even think of it as transformations. A times x minus something plus b times y minus something and so forth, yes. And then if you distribute and get all your crap on one side, the 0 becomes whatever the hell the number is. Okay, I love it. Okay. I love it. Okay. So let's get a little bit into 1-3. And the weird thing about 1-3 and 1-4 is I'm going to do a little bit of both. And this is going to be all of our task. This book is amazing. This author is one of the most amazing linear algebra instructors ever. So watching some of his lectures is amazing. You know, I could never possibly hope to be this person. Gilbert Strang is just the linear algebra guy. You with me? And I'm okay with that because it's been 16 years since I've taught this, so I'm fine. What do I want to say first? Which way do I want to go with this? The problem with the problem with the book is he's kind of very conversational and he sometimes forgets what he's not said yet. I think I've said this before. So one thing we're going to have to kind of know better for sure is how to multiply two matrices. I think the first day I did a couple quick examples, but I really want to make sure everybody understands matrix multiplication. So I want to do two things. I'm going to do something related to matrix multiplication that we can just do directly, but then I need to remind you how matrix multiplication works. So let's look at this. Couple things, some definitions first. Let's get these definitions out the way. Does anyone happen to know? Sorry. Does anyone happen to know what I wrote? Okay. Does anyone happen to know the dimensions of this matrix just by itself? I'm not asking you what dimension space or whatever, just the dimensions of this matrix. 2 by 3. It's always, now be careful, it's always rows by columns. rows by columns, R by C. So 2 by 3. So it's literally like a 2 by 4 or something, same idea. So there's 2 rows, 3 columns. Now for us, to begin with, we're going to focus on considering each column as its own vector. So how many vectors do I have? 3 vectors, and what space do they live in? R squared. 3 column vectors living in 2-dimensional space. How are we doing there? Is that okay? Okay. Is it possible that those 3 column vectors are linearly independent? What do you guys think? It's impossible. Why do you think that is? Do you agree with me that more than likely at least 2 of those vectors are linearly independent? You guys with me? But it's so
I'm just trying to figure out what that's like.
3 column vectors living in 2D space.
Yeah.
Because every vector has how many components? 2. So I'm in the xy plane, for example, right? If I'm given any 2 vectors that are linearly independent in 2 space, they can create every other vector in 2 space. That's what we said earlier today. The easiest one to do is x-axis, y-axis, because they make the pieces easy to construct. I can make the vector 3, 4 easier from 1, 0 and 0, 1, but I could use 1, 0 and 1, 1. Trying to do it from your perspective. I'm already off script. 1, 0 and 1, 1, yes? I could use those because they are still linearly independent. It would just be a little tiny bit harder, yes? I don't know if you guys are really with me. There's a question kind of like that, I think, in the homework. Yes, beautiful. So they have to be linearly dependent. There's no other way, because 2 of them would be enough to construct every vector, and then this vector's like, you don't need me, you can make me. Okay, that's fine. So this is what we call like an overdetermined situation. I've got more vectors than I need. Okay, let me stop for a minute. I still promised you, and we'll still get to a point where, given a matrix, going to determine which columns, how many are independent and which ones. Yes? I promised you we're going to get there. We will. We're just not there yet. Okay, I keep teasing you. Real quick, what do we call this? Anybody know what we call this matrix? Identity matrix. I. Why is it called the identity matrix?
It's what an X, Y, and Z for 1.
Okay, sure. But what's the identity, what's the additive identity? For example, number. Yeah, when I multiply a matrix by this, it stays the same. That's the idea. So if you don't know how to multiply matrices, that could sound very trippy. How the shit does that happen? But it does. I'm just laying down some definitions. What would your gut want to call this kind of a matrix here? Where do all the non-zero things live? All the non-zero elements live where? On the diagonal. So this is called a diagonal matrix because math people are remarkably creative. So I'm just laying down, these are going to be words we're going to use for the rest of the semester. So I can talk about diagonalizing a matrix. I could talk about the upper lower triangle. So you see this would be the lower, upper. Do you guys kind of see what I'm saying? Okay. What's special about, well, here, I might as well write this. Based on what I just said, what do you think I can call this matrix? Okay, I like it, like a lower triangular matrix, right? Because the zeros are in the bottom. So we get an upper triangular, lower triangular. So this is a type of triangular matrix, yes? So a diagonal matrix is one that just both triangles are zeros. Both triangle parts are zeros. And what do you think special about this matrix here? They're all special, be quiet. Anything special about that matrix? Poor little guy. Poor little guy. Screw him, there's nothing much special about him. Thinks he's special, ain't all that.
It's just the matrix.
I like it. He said, it's just a matrix, man. Leave it alone. So, what's the special? Can anyone see what's special about it? Anything? Symmetric. Oh, that's exactly what it is. 215, 215. If you compare going down here, 112, 442, it's symmetric. Boogie. Oh, woogie, woogie. So this is symmetric. So it's easier to see, like in 2D, it would just be 1, 2, 2, 1. That's fascinating. Yes. If I changed all the rows to columns and vice versa, wouldn't this stay the same? You guys see that? Okay. All right. So that's symmetry. That's sort of like folding something across an axis of symmetry. It stays the same. That's what that kind of is. If I switch the rows and columns, it's the same matrix. So that's a symmetric matrix. Okay. So let's do this. I want to introduce something independent of the general idea of multiplying matrices. Do I want to? Yes. And then this might actually help explain why we multiply matrices the way we do. So say I have a matrix A. Doesn't really matter what the numbers are, but I might as well use these guys. So just to give you a taste of what we're getting into, can anyone identify one column vector that's in A? Yeah, 1, 0, 0 is a column vector. There's also 0, 1, 0. There's also 3, 2, 1. Those are column vectors. Give me one row vector in matrix A. 0, 1, 2. I love it. So everything we're going to discuss about columns, we're going to focus on columns first, because traditionally, historically, we kind of built some ideas based on column ideas, but then we can build the same ideas for rows. So we have columns, and I can do linear combinations of those columns. Okay. So somehow multiplying these two, this matrix with this vector, I'm going to end up combining columns. So let's see what happens. So let me first do the row picture of this. Both ways we're about to do this, thank God, is going to come out to be the same answer. It's better. If 7 times 4 is 28 on Tuesday and 11 on Wednesday, we got a problem with math. Okay. So I'm going to do the same problem 2 different ways. Oh, by the way, let me go ahead and call this the x vector. So we know dot product, correct? So fundamentally, one way to think of matrix multiplication is dot products. If I take row 1 and I dot it with x, row 2 and I dot it with x, row 3, Jeff, there's only one row 3, and I dot it with x. And that's how I construct the answer matrix. So I really want this to make sense. Row 1 dotted with x. Yes? Do you guys see that? So what is row 1 dotted with x? In fact, real quick, before you do that, row 1 dotted with the x. So the first row vector dotted with the x vector. What's the answer going to be? I mean, not the number answer. In general, is the answer going to be a line? Is it going to be a lunchbox? Is it going to be a toy zebra? It's going to be a number. Kick ass. I want somebody to say toy zebra. So, I'm sorry, what did you get again? Yeah, 1 plus 0. Now be careful. So 1 plus 0 plus 15. Do you guys see that? So we get 16. So what's row 2 dotted with the x?
3, 7.
7. And row 3 dotted with the x? That's easy, right? Yeah. It's always nice when there's a bunch of zeros. Now, that's the row picture. So, to put together the answer to A times X, matrix times vector, I could either look at it as dotting the rows, or, so the answer better not change, just because I'm looking at it different, because it's the same problem. I can look at it, the column picture. In which case, I look at this vector as being commands as to how to combine my column vectors. The first element in X is how many of my first vector to have. The second element of X is how many of my second vector to have, and so forth. So let's see if this works out the same way. So this would be, I want how many of my first column? 1. I want 1 of these. Plus, I'm sorry, in this case it'd be minus the negative 3. Plus negative 3 of 0, 1, 0. Plus 5 of 3, 2, 1. So then I end up with 1 minus 0 plus 15 is 16. Is that cool? 0 minus 3 plus 10 is 7. 0 minus 0 plus 5 is 5. I get the same name answer. Okay. This is the way it's actually done more often. When you first learn how to multiply matrices, you sort of automatically do row times column, row times column, row times column. Okay. And remind me, how big is this? What's the dimensions of this? 3 by 3. What's the dimensions of this? 3 by 1. These two are the same, so I'm allowed to multiply them because I better have these match up with these. And how big is the answer? 3 by 1. Either way you do it, same answer. Okay, I like it. Oh my God. I don't know. I feel like our perceptions of time in here are probably different. For me, time flies. For somebody who's like, Lord, get me out of here. Okay. Couple more things, then I'll let you out. Okay. Then I think I probably spoiled you the first 2 times. Too bad. Don't get used to it. Yes. Remind me about this. If A has linearly independent columns. Oops, sorry. Then what's the only way you can get AX equal to 0? Assuming neither A or X are 0. Okay.
What's the word after has?
Oh, I'm sorry. This is my quick way to write linearly independent. Because I'm going to write that a lot. So I'm sorry, I just did it without. I see that and it says linearly independent to me. Does that make sense? Anything I could do to write less is good. You guys live that every day. Yet you're with me. Okay. I like how some of you guys are just, yes, this is true. So just to remind you guys, this would be like sum A, B, C, D, E, F, G, H, I times sum x1, x2, x3 equals 0, 0, 0. Say again? What do you mean normal? Not sure. Oh! I said nothing about anything being perpendicular here, right? I just told you that they're linearly independent. What's the only way, do you think, that I can get? So if I multiply this out to get AX1 plus BX2 plus CX3 equals, just by itself. So I need this to be 0. And I also need this to be 0. And I also need this to be 0. Yes? So does anyone have any idea what's gotta be true? What's the only way I can get that to be true?
X 1, 2, and 3 are all 0.
X1 equals X2 equals X3 equals 0. Exactly. And this is something we call the trivial solution. So if I have a matrix times a vector where not all the elements are 0, or else, come on. The only way that could equal 0, 0, 0 is if I feed it 0, 0, 0. Okay. If they're not linearly independent, there will be other ways to make that happen. So, a quick concrete example. Yeah, perfect. This is perfect. Sure, Jeff, whatever you say. I should show you. I really don't like the projector, but it's okay. Very quickly, and again, I promise you that if I ask you a question about linear independence before I give you the shortcut, I'm going to make it obvious. Can anyone see why those column vectors are not linearly independent? Add the first two. You get the last one. Or you could say the last one minus the middle one is the first one. You could say that a billion different ways. You guys all with me? So they're obviously not linear. So there could be, there has to be a way to get this to work that where A, B, and C are not all 0. So let's see if we can do this real quick. This will be the last thing we ever do in our whole life. No, just for tonight. This will be A plus 2B. Is this cool? Bam, bam? Like that. Shaboom! Yes? Now, can anyone give me a good thing to do here? There's a few different things you could do.
You can make A equal to negative C.
Beautiful! I kick ass. So anytime there's already a variable missing, that kicks so much ass. So then, therefore, if I subtract 6C, divide by 6 to get A must be negative C. Yes? So what does that mean I can do with this first dude? If A is negative C.
You can plug it in.
So if I put negative C, that makes 2C, that makes 2B plus 2C equals 0, which means that B is equal to
Negative C.
negative C. And if I do it here, this will be negative C plus 4, it'll be 4B plus 4C equals 0. I get the same thing, yes? So as long, now this is trippy. I really want you guys to, as long as C is C, A is negative C, and B is negative C, that is a solution. So how many solutions are there? How many values of C can you imagine? Infinite number, right? There's some you can't even imagine. So give me one answer out of the infinite sea of answers there are.
C equals 2.
If C is 2, what's A?
Negative 2.
And what's B?
Negative 2.
Okay. So anything that looks like that, any multiple of that, any, how do I want to say this? Yeah, any multiple of that. So whatever you let C be, A and B are determined. You guys kind of with me. So, as we move, oh good, I got more time than I thought. It's 5:20. That's when we end, right? Yes. Sure. I'm sorry. The light on that's making me trip out. I appreciate that. Keep me honest, guys. That's enough. So as we move through the semester, we'll talk more about the size of the space of the answers. Do the answers live in a plane? Do they live in a line? Do they live in a space, three-dimensional space? So that's enough tonight. So next time, remember, Wednesday. I'll see you Wednesday. I mean, a week from Wednesday. Not this Wednesday.